So, besides energy storage, as well as transmission upgrades and natural gas combined cycle plants, another option that could be useful in helping to integrate large amounts of variable renewable energy is demand management. And so, this is essentially all this means is customers changing their own behavior in order to align the timing of electricity consumption more closely with when renewable energy like wind and solar is more naturally available. And so, this could be facilitated through two different types of programs. One would be real-time pricing, and the other would be demand response. So let's talk about these. So both fall into this category of smart or flexible demand that we've alluded to before, as potentially an integral piece in helping to facilitate the deeper penetration of variable renewable energy into the grid. So again, both real-time pricing and demand response does not necessarily mean that customers are reducing their electricity usage. It's more about altering their electricity consumption patterns. So let's talk about real-time pricing first. This is an effort to get end-use customers to actually experience more of the natural variability that exists in wholesale electricity markets. So remember, we've seen this figure before. This is our from our conversation about the history of the electric power industry, and so that what this is supposed to illustrate is the operations of a wholesale electricity market, retail electricity distribution companies, and then also retail customers. So we're way at the bottom here, right? Utility one retail customers, that's you and me and everybody that we know. We buy electricity from retail distribution companies. And in the case of North Carolina, that retail distribution company is Duke Energy. So it's a vertically integrated regulated monopoly. So that's not what we're talking about here. But in most of the United States, the retail distribution companies that sell retail electricity customers energy are then in turn buying electricity from a wholesale market where different generators or power plants are competing with each other on the basis of cost in order to provide electricity. And in the wholesale electricity market, prices are going up and down all the time because you have the system supply curve interacting with demand. And demand, as it fluctuates throughout the day, is causing that price of electricity to go up and down and up and down. And so prices are high during some periods, during peak periods, and low during others, during off-peak periods. And so that's what this figure shows here. The sort of natural price dynamics in wholesale electricity markets look a lot like the fluctuations in electricity demand. However, many retail customers don't experience this. And that's sort of by design. From the early stages of the electric power industry till today, retail electricity customers have really been shielded by the natural fluctuations in the cost and the price of electricity on sort of the grid scale on the wholesale level. So we've talked before about what retail electricity consumers see on their electricity bill. And there's two different charges. There's fixed charges. This is sort of like the connection fee, right? It's the amount of money that you pay every month to your utility just to be a customer, right? And so this would help them cover meter reading, billing, administration costs, and maybe other fixed costs associated with maintaining the grid or paying for power plants. And then there are other types of your electricity bill that vary with how much electricity you use. Those would be volumetric charges. So the more electricity or kilowatt hours you use, the more electricity you're going to pay on that part of your bill. And we did talk a little bit about before the fact that sometimes volumetric charges can be time of use, which means that during certain periods of the day or the year, the dollars per kilowatt hour or cents per kilowatt hour that you pay is different, right? And so this is an example of a time of use pricing scheme for a utility in California called Southern California Edison. And what you'll notice here is that you have two different seasons, summer at the top, winter at the bottom. And then in each season, you have different price schedules for electricity depending on whether you're on the weekday or the weekend. So take a look at the weekday in the summer. Of course, electricity demand in the summer is highest in the middle part of the day. A lot of that has to do with increased demand for cooling. And so what we see here is that electricity costs 46 cents per kilowatt hour during this period of 2 p.m. to 8 p.m. during the weekday in the middle of the summer. And it's cheaper in other parts of the day. And so the point of that is to try to mimic the sort of natural variability in the wholesale price of electricity in California, because Southern California Edison is buying electricity from the wholesale market and then just delivering it to retail customers. And so by creating price schedules that vary throughout the day, they're trying to expose customers to some of that variability. So a lack of true real-time pricing in retail markets actually limits the potential for customers' price elasticity of demand to help shape their patterns of electricity consumption. So this is something that we talked about early in the semester. Price elasticity of demand is essentially a way of measuring how a given change in price impacts demand. And so we quantify it as the ratio between the percentage change in quantity demanded of something, in this case electricity, divided by the percentage change in price. And there are different sort of categories that we would put this in. If you had a price elasticity of demand that's infinity, that would refer to perfectly elastic demand. Between infinity and 1 would be elastic, which means pretty sensitive to price. An elasticity of demand equal to 1 means that for any percentage change in price, you would get an equal percentage change in demand, a decrease in demand. A price elasticity of demand between 1 and 0 means that it would be price inelastic, which means that a 1% change in price would result in a less than 1% change in demand. And then a price elasticity of demand equal to 0 means that it's perfectly inelastic, which means that even if price changes, demand won't. And so remember that if we have a demand curve that looks like this, we can break it up into different segments, A to B and B to C and C to D. And we can actually calculate the price elasticity of demand for each one of these segments. And so for that demand curve I just showed you, we can calculate the price elasticity of demand in the right-hand column here. And what this shows is that for different parts of the demand curve, there's different price elasticities of demand. And so in layman's terms, what we see here is that when price is really high, which would suggest the segment C to D as opposed to A to B or B to C, then a 1% change in price results in a greater than 1% change in demand. Whereas if price is pretty low, and that might refer to the segment A to B, then a 1% change in demand results in a less than 1% change in demand. So when we've talked about wholesale electricity markets, one of the things that we've noted over and over again is that we've treated essentially demand as perfectly inelastic. That's why it's perfectly up and down. And that kind of makes sense to do in wholesale electricity markets right now, because demand for electricity has not been traditionally responsive to price. Think about it. When you are using electricity, are you thinking about price at all? Actually, the signal is going from you as a consumer to the power plants. When you demand electricity, it's up to the power plants to immediately respond to that. There's no information coming to you about what the price is and influencing your decision. However, there are potentially huge economic benefits associated with real-time pricing, much of which could come from peak load reduction. So let's talk about that a little bit. So peak load reduction would essentially mean that during the hottest parts of the year, people use a little bit less electricity. So what would be the benefits of that? Well, one of the main ones would be that we might just need, it might allow us to rely on less physical capacity. If we think about a system supply curve made up of different power plants shown here, they all have different costs, right? And we've talked about how the most expensive power plants that we have in the system, all the way to the top right, for example, diesel oil generators, are probably the most expensive in terms of their marginal cost, right? So we usually consider those to be backup capacity. We only use them if we absolutely have to. But traditionally, we've needed those power plants to be on the grid just in case, right? There might be 1 day per year or 3 hours per year where that capacity at the very top right of the cost curve gets used. And we need it in order to ensure 100% reliability. Now, what that means is that we're building power plants that we still have to pay the fixed costs for, the debt service, in other words, the mortgage for, that we're really only using about 1% of the time, right? And so that adds an expense to maintaining the reliability of the grid that maybe we could eliminate if demand was a little bit more flexible. In addition, the shape of the system supply curve, which is much steeper at high levels of energy production, means that even small reductions in demand during peak hours can result in much lower electricity prices. So I'll give you an example. So let's say that peak demand is that yellow line all the way out to the right. And we just reduce peak electricity demand by maybe 5%, right? And so let's say that a 5% reduction in peak demand shifts peak demand just a little bit to the left, right? So that would be that second yellow line. So for a pretty small change in demand, what we get is a really, really big drop in the wholesale price of electricity, which is the vertical difference between those two green dotted lines. So those are benefits from real-time pricing without even considering how we would use this to integrate renewable energy. But real-time pricing also could be used to incentivize customers to use more electricity when the sun is shining and to use less electricity when it's not. And so the example from California has to do with the duck curve, right? So what this shows is the progressively lower net demand for electricity in the middle part of the day in California as the state incorporates more and more solar power. So what this is doing is it's driving the wholesale price of electricity down in the middle part of the day in California. The more solar that's put into the market, the lower it drives the wholesale price of electricity during that middle part of the day. And so if you could expose actual retail customers to this, right, then there would be this incentive for customers in California to use as much electricity as possible of their normal electricity usage during the middle part of the day when the price is lowest, and to actually minimize the amount of electricity they're using after about 7 or 8 o'clock in the evening. And so this might be a little too much for the ordinary customer to think about, but one of the advantages of new technologies is that potentially our electricity usage from different devices could be automated. For example, if you had different devices in your home that were connected to the internet, and they had some information about what the price of electricity was during the day, maybe you could program your air conditioner or your water heater or your washer or your dryer to only consume electricity in other words, to only operate when the price is below a certain threshold.